Now I would like to introduce the differential form of conservation laws. And you remember from our previous lectures that we have talked about the integral form of continuity momentum equation, and we applied those equations to solve several problems. Now I would like to represent those equations in the differential form. So let's start with the continuity equation first. So in the continuity equation, you can see it's a well-known equation, you all know that. Now I would convert this equation in the integral form utilizing some mathematical relations. Now first look at that equation, the continuity equation. In this equation, I have two terms. One term is the control volume and the other one is the surface integral term. So the idea here is to convert this surface integral into volumetric integral, and in order to convert that I have utilized the Gauss divergence theorem. So utilizing this theorem, this term has been converted into a volumetric integral. So I will go and substitute this value in place of this in this equation and solve for it. So you have seen that I have obtained this equation once I perform the substitution in equation, if I call it equation star. So that equation has been come here like that, and since now both terms are on volumetric integral, so I can take this as a common out and subsequently simplify this. Now upon simplification I have obtained this equation. In this equation the integral this control volume CV integral is comprising of this term. So this is integrand. So if the integral is 0, then integrand should always be 0. So this will implies that I have obtained the following differential form of my continuity equation in this way. Make sure it is equal to 0. Yes. Remember, in that equation this del is the del operator and it has a definition this, where v is the velocity vector. For 3D flow it can be written like that. So that's our definition of these vectors. So upon performing this dot product, I will obtain an expanded form of the continuity equation that I will write down now. So you have seen that this is another way of representing my continuity equation. So next I would like to mention about the momentum equation in the differential form. Again I will write that. So earlier we already have this equation in the integral form, and you have been utilizing that equation for solving several problems for finding the drag or thrust. That's how we did. So now we will go and derive the differential form of this equation. So as you know from the basic law of Newton, that the external forces are equal to the rate of change of momentum. So that's how I write this down here. So left hand side is the summation of the external forces acting onto the body. So those external forces are your pressure force, it can be pressure force, body force due to the weight of the body, and viscous force due to the friction, that shear that acts. So that is the left hand side, and the right hand side will be the integral form of the equation that we already have. Now further details of the left hand side of this equation. The pressure force, as all you know that pressure is acting normal to the surface area, so multiply by normal vector and the area, you can easily get the pressure, and negative sign pressure will be on to the surface. And similarly this is the body force, which is density and specific volume. So now in this equation that we have, again we will perform this, that we will convert all the terms which are on the surface integral into the volumetric integral. So we will convert this term and this pressure force, this term needs to be converted into the volumetric integral such that I can take them out common and then perform the same procedure to obtain the momentum equation. So let's go and do this for the pressure term first, and next we will do this for the integral term on the right hand side, this term. So now I have converted the pressure, which is onto the area, into the volumetric integral utilizing the gradient theorem, and will substitute this into the momentum equation. Now also note that momentum equation is the vector equation, so I will consider only the x component of that equation for my analysis, and subsequently that can be extended for the y component and z component. So I have substituted the values of my pressure term here, which is onto the control volume, the body force x component already onto the volume, viscous force always onto the volume, and only this term needs to be converted onto the volume. So to do that, I will again go and utilize the Gauss divergence theorem. Now subsequently, after transforming this term from the control surface onto the control volume with the help of Gauss divergence theorem, I have substituted back this term in here and take this integral common. So that is the previous equation that I have. Now further simplification, putting all those terms on one side, have provided me this form. So in this form, the integral will only be 0 if the integrand is equal to 0. So using this basic technique, I will go and further write down this equation in the differential form. Now further rearrangement has resulted in this form of the equation. So this equation is the differential form of momentum equation and the x component of it, and it is equation 2.70a of your text. So it is my Navier-Stokes equation in the differential form. Now from this equation, I can also further derive an equation commonly known as Euler equation for my ideal fluids, that is when the viscous effects are negligible. Viscous effects are negligible, so the fluid flow is known as the inviscid flow, or also ideal flow, that is no friction involved, ideal fluid. So for the ideal fluids, the viscous force will become 0 and only the equation I will have, I can write down that. So this equation is my Euler equation for unsteady flow, and this equation is my Euler equation for a steady flow. Call it Euler equation. So here is another equation, Bernoulli's equation, that exists for ideal fluids, and this equation can be derived from the Euler equation, and this equation includes pressure and the kinetic energy due to velocity. So for any point in a fluid, for example, if I have 2 points, different point 1 and point 2, so this part will always remain constant to each other. So that's how I can write down this equation for 2 reference points. Again, we will utilize that equation for determining the pressure or velocities when we will go and talk about the ideal fluids or inviscid part of flow fields.